Well, number one, I want to say thank you. I mean, I know it's hot out there. There's a lot going on. And the effort is greatly appreciated by everybody. Number two, we encountered some issues still with splatter and things like that. And as part of our ongoing commitment to further the people and further ourselves become better, we teamed up with Lincoln today, who is also participating in sharing the bill for lunch with us. This is Michelle. She'll kind of start you guys off.
Okay. Good morning, guys. My name's Michelle Adams. I'm with Lincoln Electric, and I'm based out of Charlotte, North Carolina. And I've been with Lincoln for 15 years. I'm originally from Ohio. Don't hold that against me. I'm by degree a welding engineer, but by trade I'm just sales. I don't have the skill that you guys do. I know what it sounds like. I know kind of what it looks like, but I don't have the helmet time. So I do know what it takes, but I don't necessarily have the skill. But I'd like to come in and show you guys a little bit about kind of what you're seeing. I think this class, just spending some time and explaining the different variables of what goes on in welding. Sometimes if you see it, and somebody takes the time to explain it to you, it makes more sense. Sorry. So I've done this class many times, and I've had folks afterwards that come up to me and say, hey, listen, nobody ever took the time to explain to me exactly what each of these knobs did. I kind of just mess with it until it comes out right, but if I'd have known a lot of what was told here, he said, I would have been a better welder much sooner. Okay? So I do try to keep it interactive. So if I call on you, give me some ideas, some answers, and I think that way it keeps it more active and everybody learns a little bit more. Okay? How long has everybody been welding? A while? 5 years? 10 years?
17.
17 years. Okay, what's the newest one? What's the youngest one? A year? Anybody 2 years?
I had about 3 years before I came out here.
So you're fairly new. A little bit. Okay. All right, so we're going to assume that you guys don't have a lot of welding knowledge, and let's start from ground up. I don't want to assume anything, okay? Let's start out, first of all, the basic parts of your weld. All right, who can tell me what A and A would be here as well, what that part would be? These are important terms because when Mike tells you, I want you to watch this or correct this, you need to know when he says that, what he's talking about. Because if you guys aren't communicating on the same plane, nothing ever gets fixed. Okay? So what's part A, if you had to guess?
Wall.
A wall? Anybody else?
Weld face.
That's a toe. Toe of your welds. Okay? So when you're watching and you've got, and we'll talk about this maybe later, a little indication here where you've got a little dig right along there, and you say it's undercut. You heard the term undercut? Undercut always happens at your toes. Okay? Who can tell me what this part is right here? When you look at it, what do you look at?
Face. That was what I thought you were talking about a minute ago when I said weld face.
The face is always what you look at. When you're done, when you look at it, you're looking at the face of the weld. You always want that to be what they call a flat face. If you can get it fairly flat, great. You never want a concave where it's caved in. And if you get a weld that looks like this, it's really kind of a waste. It's okay, but it's a waste because the only thing structurally that helps you is just this area right here. So all that extra is wasted time and wasted filler material. Okay? All right, what are these? What's this dimension here? What's this and that? What do you think your weld stands on?
Weld joint.
What do you stand on?
Base. Base.
Those are your legs. Okay? Ideally, if you've got your torch angles correct, everything's at 45, if you come right in here and split that difference, This leg should be equal to that leg. If it's not, if your torch angle is off, and you may get a weld that looks like this, maybe you're hitting down here, right? So now this leg is going to be much longer than that leg. So again, that's a waste situation because all that structurally would be through here. So this is the only part that's used. Okay? So you want equal legs. All right, and the most important, what is this little area right there?
The heel. Heel.
The heel? No, close. When you say, when you put your weld in, what do you want to hit? You always want to hit the, you ever heard the term root? Okay? So when you come in at an angle or the joint, you always want to go right in and hit that root. If you make a weld, and I don't know, have you guys ever done like micro or macro etches? Cut a weld and looked at it?
We haven't done it physically here, but we looked at a
Okay.
video about it.
I mean, if you have a, let's say a T-joint, where you have a plate, looks like this, and you put your weld in, and let's say you cut it, you make a long weld, and they put it in a chop saw and cut it in half, and then you look at it from the side. Sometimes what you'll see if you don't hit the root is it'll kind of look like this. And there'll be an area right there where you didn't get enough penetration. And they say that you didn't get your angles and you didn't put your torch right into the root and hit that and burn that. So I could see air right through that bottom of that corner of the weld. It's very important that you hit that and get good penetration. Okay? So if Mike says make sure you follow your toes, make sure your legs are equal, everybody kind of makes sense now a little bit? Okay, what variables do we have in welding? I've listed the major ones. Does everybody understand this means wire feed speed? Okay, so you've got, this is a knob, and this is a knob, right? Those are the only two knobs that you've got. Now, if you're welding and your buddy says, give me more heat, I need more heat, which knob are you going to turn for your buddy? You're turning voltage.
Voltage.
You're turning voltage.
Wire.
Voltage? Voltage. That's your heat. Okay? This is your penetration knob. If you get nothing else out of this, understand the difference between these two knobs. Wire feed speed, always and forever, controls your depth of penetration. As your wire comes in, it controls how far below the plate that's going to dig. So this, I call this dig. Imagine a water hose. You turn the water hose up and you hold it into a mud puddle or dirt puddle. And the faster you turn that water on, the more it's going to dig down into that puddle, correct? Same thing with your wire feed speed. When you want more dig and more penetration, you're going to turn up that wire feed speed. Okay? So remember, wire feed speed controls this dimension in your weld. Now, voltage is heat. Voltage is going to control this dimension. Okay? And let me explain why. You got 3 plates here. Okay? You got 3 torches. I'm assuming I can't see if they're all the same arc length, but let's say this one is at 25, this one is 27, and this one's 23. All right? So 25, you got an arc length that looks like this. Maybe a puddle looks like that. All right? Now your buddy turns up the heat. 27 volts. Now what happens? You got a longer arc, right? Assuming, now this is assuming that you're steady. It's assuming that you're not doing this while your buddy's turning the knob, because otherwise you're messing up, okay? I'm assuming that you're keeping a steady arc. When you immediately jump up 2 volts, that lengthens that arc length. So your arc length went from here up to here. But understand what that does. When your arc length gets higher, what happens to your arc cone?
Why?
It gets wider, right? So that's why I say it controls this dimension. So as you go up in voltage, your arc gets wider. But what happens underneath? You only got so much energy, right? You got so much energy that goes into that puddle. And if the energy is up top, there's not much energy underneath. All right, so what's going to happen with this one?
It's gonna be smaller.
It's going to be smaller, it's correct. It's going to be shorter, so your arc length maybe is going to look like that. It's going to have a real narrow focus cone. What's going to happen underneath?
It's gonna be wider.
It's going to be deeper, right? The energy's got to go somewhere. So if the energy isn't up here, it's got to be below. Right? So this is what arc length does. Your arc length and your voltage now went from here, instead of here, it went shorter. Does that make sense to everybody? So voltage is going to control what dimension? Your width of your puddle, right? Wire feed speed is going to control your depth of penetration. So if you're looking at your weld and you don't see a wide enough weld, if you see a weld that looks like this, which knob are you turning? Why do you say, who said wire feed speed? Okay, why would you do that?
Push it on down there.
I'm sorry?
Push it on down in there.
Push it down in there. Okay, when you get a weld that looks like this, as opposed to a weld that looks like this, this is kind of humped up, right? When you get a weld that looks like it's not wetting out,
Cold, isn't it?
yeah, it's cold, right? So what do you do when it's cold?
Turn up the heat.
Turn up the heat. So what you do is you turn up your voltage a little bit. And not so much as in general, a half a volt. As a rule of thumb, a half a volt will get you to wet it out a little bit. Okay? So you go 25, maybe you would try 25 and a half, 26 volts, and see how that works. Okay? Next thing is your travel speed. Travel speed is how fast your hand's moving. So if you're moving at a slow speed, you're probably going to look like this, right? If you're moving a little bit fast, well, if you're moving too fast, this is too fast, sorry. And when you slow down a little bit, it gives the heat a chance to wet it out. Okay? So if you go really fast, it looks like you just laid down a rope, doesn't it? So, a lot of these, in truth, a lot of these variables all kind of knit together. So it's it's tough to say just one variable will fix your problem. It may be you look at your weld and say, it's kind of roped up. I can either turn up my voltage a little bit, or I can turn down my wire feed speed. And that's where maybe you get with Mike and say, hey, or I can slow down my travel. Ideally, we like, welds like to be hot and fast. So if you can turn up your voltage a little bit and travel, that's the way you should go. You're going to get more productivity. Company makes money, everybody's happy. We keep jobs, we keep more business coming in. At the end of the day, guys, it's about making money. For you, company, everybody. So quality makes a big difference. We can do the right thing, figure out what the issue is, figure a way to speed up production, everybody wins. Okay? So travel speed. When you're looking through your helmet and you start seeing this with your weld, and you're heading this direction, what's that mean? When your these are going to be your toes, right? Of your weld. You see that glowing worm, right? When you're welding, you want to stay on the front edge of that puddle. You want to stay on the front edge going this way. Don't get back. There's ripples the whole way. Don't get caught in the back side of that puddle. It doesn't sound right. It doesn't have that correct crackle. If you stay on that front edge of that puddle and you're going forward, it'll make a big difference. Now you guys are running straight stringers, right? So you want to put a little bit. Here's dead center. You want to be maybe 10 and you want to push. You always want to push. I was taught if it has a slag, you know, how many are stick welders? You know, you always drag stick, right? Slag, drag. That's what you're taught. But if there's no slag, then you always push it. So a push means your torch is this way and you're going this direction. Okay? Your gas is flowing this way in front. The bead tends to have a better profile when you push. Can you pull it? Yes, but it's not preferred. Okay? When you pull it, your torch is this way, but you're heading this way, your gas is down the way. So guess what gets sucked in on the front? You get air sucked in the front usually. So it tends to rope the bead up a little bit more. If you have to, maybe a pull, you know, would be okay, but preferably push. Okay? Torch angles, we're talking about at 10 degrees off center, and then you always want to split at a 45. So this is a 45 degree if possible. You guys don't do multi-pass, correct? No multi-pass welds?
Only if necessary.
Only if necessary. Okay, so if you did a multi-pass weld, you do this one would come in right at about a 45. Now the next one you're going to put down here, and you're going to come down probably like this. And you would want to split that difference and maybe come in here. All right, so you always want to make sure you split that difference, maybe 45, and then tilt it back 10 degrees, and then go ahead and pull your trigger. Okay? Does anybody have an idea, just for kicks and giggles, how hot that arc is? The reason I say is when you pull that trigger, you got to know what you're doing with it, because that arc's going to burn something. You got to know. You're dealing with thin gauge metal. If you don't have an idea where you need to end up and how fast your welds are fairly short. You got to know where you're going. You got to know where you're going to be there, and move with it. How hot do you think that arc is?
4,500.
Close? Higher?
7,000.
Close. 6,700 degrees. It's hot, gentlemen. Okay? I don't know how they measure that, but that's just for a reference. Steel melts at about 2,700, 2,800 degrees. All right. Let's see, what else? We talked about heat being equal to your voltage. How about defects? What's the most defects you guys see?
Porosity.
Porosity? And what do you think causes porosity?
Not enough gas. Too much
Oxygen getting into argon fuel.
Those are all, yep. Let's start with the first one, porosity. The biggest you guys face, I think, what you said was spatter. And porosity. Okay, so porosity happens it's either a arc length issue. Okay, so if your arc length is too long, you lose your gas coverage, right? So your arc length could be a problem. You could have gas either lack of or, believe it or not, too much. Does that make sense? Do you understand why too much gas? Everybody says, well, I want the fan on me, so if I turn the gas up a lot, that way I know I got gas, and everybody complains about the fans blowing away my gas. So the problem is when you turn your gas up really high, you've got this gas coming down, let's say at a certain speed, and ideally it's supposed to do that, right? But if you get it, again, like a water hose, you get that gas flowing at a high speed, it comes down, it hits that plate, it goes back around, and then comes back into the puddle. Guess what it grabs out here?
Yeah.
All right, they call this the Venturi effect. Okay, so it comes out on both sides. It does this and throws the oxygen right back in your puddle. All right. So too much is definitely not a good idea. What's your spec? What do you call out? 30. Do you guys know what it is?
I normally run mine between 35 and 45, depending on what I'm doing.
And that's probably fair. I don't know, I mean, there should be somewhere out there, or Mike should have specs or somewhere listed for what you guys need to have. Does everybody set their own? Is it on a manifold? How is that set?
It's not on a manifold, it's on an individual machine, we run tanks on the machine.
Okay,
The
so,
rule of thumb is anywhere between 25 and 45.
okay, that's fine. But, you know, just be aware of it, so don't go any higher, because this is what's gonna happen. Now, another thing, let's say that you have everything set right, and let's say your gas is at, let's say 35, 40, and you're still getting porosity, your arc length is set right, what else could be wrong?
Angle.
Your angle could be wrong, that's right. You could be maybe if you have an angle that's like this,
Just blowing over.
and you're heading this way, you know, your gas is going sometimes way out this way, and not necessarily down. Okay, so too much of a torch angle could be a problem. What else could give you if your gas is set right, what else gives you porosity?
Too much air flowing over too well.
That could be, yeah, if you're by a door and you see a lot of cross ventilation and you see something blowing away your gas, that
What
could
about
be.
trash?
And that's a good thing. If you're welding over a mill scale, a lot of mill scale, or oil, if you get some oily parts and you weld over top of that, you're gonna see a lot of spatter, a lot of smoke.
Paint,
Yeah, paint, any contaminations. So if you see a lot of that, I don't know, do you guys grind? What do you do?
we usually grind the paint off, or if we have we don't really experience real heavy mill scale.
Okay,
It's
so
more the decontamination or
the good thing about carbon steel is that any protective layer, every metal on Earth has a natural tendency to protect itself with something. Okay, for carbon steel, it's a rust. You see, carbon steel, in order to protect the steel itself, it puts a rust coating on the top of it. And stainless steel does the same thing. It has an oxide layer on it as well. Aluminum's really bad. Aluminum will put an oxide layer on it. But luckily for carbon steel, the oxide melts at a much lower temperature than the steel. So that's why you're able to burn away rust. But if how many have welded aluminum? If you don't get aluminum clean, what happens? And you know why? That aluminum has that coating on it. It has that covering on top of it. It protects itself. That coating doesn't melt. It melts at a higher temperature than the plate. You're not going to burn through that coating. You got to physically remove that coating. That's why you'll see that scale or that scum floating on the puddle. That's that oxide that's going to catch up with you when it solidifies. So if you don't take some kind of cleaner or something, it's going to stick with you. Okay, so be aware that contamination, anything, your oils, stuff like that, if you can grind those off, clean it up a little bit, you're going to be better off. Okay? Also, another trick that's kind of easy is if you can clip, I know it's a pain, but if you can clip your wire, sometimes you get a big ball on the end of it. Well, the ball on the end of that, sometimes you'll see glass, it has the end of it, it's contaminated a little bit. Sometimes it's hard to start because doesn't have a fine point of contact. When you go to start and it's a fine point, that energy transfers across that one point as opposed to that point. So if you can cut it, snip it, sometimes that'll eliminate that pop before it starts. That will help. Okay? And also be aware, I don't know, are you guys in charge of your guns? Or in charge of maintenance for the guns and all that? No?
Just for the day, as you working through the day, you gotta keep the slag off, keep it.
Right. And everybody knows your gun's not a jackhammer, right? So you're not using your gun to beat stuff and to line stuff up. You're not supposed to, but I can go out there right now and probably pick out the guys that are, right? Because you see the neck of that gun's all chewed up. Okay? So just be aware that, the guns, if the guns are not pushed all the way into the bushings, I've seen it where they'll take those guns loose. When you pull those guns out on the barrel, there are 2 rubber O-rings, okay, and they're holes, they're gas holes in here. That's where you get the shoulder of your gun. And your liner and your wire runs right down through the center. If you don't push that gun all the way on to that bushing, and let's say you only push it in this far, the gas is not going into your gun. Okay, I'll try to show you that when we get out there. But make sure that if maybe the guy before you, if they put a new gun on, or maybe somebody yanked it accidentally, make sure you push that gun all the way in. Okay, tighten that down. The other thing to be aware of is make sure that you guys are on cylinders, right? Make sure that your lines don't have any holes in them. I've seen this before too, where we're still getting frosty. We've checked everything. We've gone through liners. We've gone through everything's fine. And they see that line, the gas line from the tank to the machine has little small holes in it. It's sucking air. Not only is it blowing air out, it's also sucking oxygen in. Okay, so check that just in case. All right, spatter. What causes spatter?
Wire speed.
Wire speed. I'll agree with that. In which direction you go. If you see you get a lot of spatter,
Turn it down.
I'll agree with that. So you're going to turn your wire feed speed down a little bit. So if you got too much and you keep hammering that, and you'll feel it. You ever feel it when it pushes back on you? It means you got way too much hitting the bottom of that puddle. It's called stubbing. You're stubbing the bottom of that puddle. You can either turn your wire feed speed down, or what else can you do to correct that?
Turn your bolts up.
Turn your bolts up. The bolts will melt it off. The heat melts it off. So ideally, if you think your wire feed speed is in the range that you need to be, maybe again you turn your wire feed, your voltage up half a volt, and then all of a sudden it smooths out. You can hear it, right? You can hear it right when you're right on that edge, and you get that nice crackle, not a lot of spatter.
Like you throw a piece of bacon on the frying pan.
Yes. I like to call it Mad Hornet. When you get on that edge where it's just not quite a spray. Have you ever gotten so hot that it turns into a spray? It's quiet.
That's all they do over at SMF is spray art.
Spray, well, that's good because they're on thick stuff. That's fine. Spray is great when you're on a quarter, a half inch, or an inch thick plate. But when you're on thin gauge, you can't do that. So you want to be right on that front edge. You want to get to that spray, then back it off. So it's kind of like a almost. Okay? That's what we want to hear. Okay? Spatter also is affected by your arc length. What arc length do you guys carry? What's your distance?
Anywhere from a quarter to a half inch away.
Quarter to a half. Okay? What about you?
Same about a quarter.
The same? Anybody else any different? Quarter to a half? Quarter's short, but I'd say probably 3/8. Something like that's probably a good rule of thumb. Also be cognizant, guys, of the fact that I'm not sure how your tips and your nozzles are, but some of them have a recessed tip. So your tip will be up in here, and your wire comes down through here. Don't forget that you've got a distance that's up in here too. So now, I mean, they call this is what they call a VSO, a visible stick out. And then you've got this distance here to here is they call it contact tip to work distance. All right, so if you buy what they call recessed tips, so the tip is recessed up in there, maybe a quarter inch. So maybe you go a half inch from here to here. Just be aware, because sometimes tips, you can buy them where they're flush, right to the edge of the nozzle. So that little distance sometimes makes a difference. So just be aware of that. Okay, what else causes it? Arc length, what else? What else causes spatter?
Moving too slow.
I'm sorry?
Moving too slow. Staying in the middle of your puddle.
The middle of the puddle, yeah. If you get swallowed by the puddle, sometimes it will. So if you stay on that front edge, it may sound a little different, but when you're back in the back, it will swallow you, and it may cause a little bit of spatter because you're popping all that liquid metal out. What about arc length? How does arc length affect your spatter?
If you got a very, very small arc, it's going to pop and crackle more and throw out more of your puddle. I mean, if you've got a large arc, it's just going to glide right over it. That's when you get into the spray oil.
I think you just got to kind of look at each situation a little bit individually. Look at make sure your angles are right. Make sure your travel and your work angle. There's a work angle and there's a travel angle. Make sure that's right. Make sure your contact tip distance is correct. And that should eliminate the bulk of your spatter. Contamination, again, that could cause an issue. Another thing that causes spatter, and I know that you guys don't think about, but just in general maintenance, how often do you change your contact tips?
When needed.
When needed, okay? So what's that mean?
Depends on how hot we're running, how fast we
So when do you think it's needed?
About every other day.
Every other day. What makes you say, okay, today's the day, I'm just gonna change it?
Just run like crap.
Yeah, it runs like
Runs
crap,
like
wire,
crap. Okay,
wire
let's-
jumps around.
So you can tell that inside the tip, stuff starts accumulating and making it where the wire won't feed out.
Okay? Contact tips in general, now not all contact tips are the same, right? You've got some tips that are designed and thicker, but in general, you got a contact tip, and they're generally oversized. You guys run all 035, is that right? Okay. So if you look at the end of this, you're going to see a hole that should be a symmetric hole. Right? If you're running 035, that should be a little bit bigger than an 035. Now, the biggest thing that I see is when you're done, the contact tip, for me, when I start getting a lot of spatter and I get bad starts, when you start hearing it go dut 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 dut, and it wants to spatter a lot,
The hole's gotten bigger.
your hole's gotten bigger, right? So the hole went from this to maybe it looks like this. Okay, and why is that a bad thing?
You don't get good welds.
Well,
Wire moves around.
What
too much.
happens, what physically happens when this wire comes through there, it makes contact. That's where the electricity is transferred from the wire from the tip to the wire. So if my hole is this big and my wire is this big, when it comes through, the wire's going dut 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 dut, and it's trying to keep a constant source of energy going through there, and it can't. So, but when it's a solid size and it comes through and it's making good contact, then you're going to have a better chance of getting stable arc. Does that make sense? The other thing that could happen, and hopefully it's not, is to, maybe look at your guns. Your guns ever get really hot?
Yeah.
If your guns get extremely hot, what amp guns are you running? 300?
300 on the Millis.
So we might need to think about going up to a higher amp gun. Okay, guns are rated by amperage, and for our guns, if you look along the length of the gun, there'll be diamonds that look like this. Okay, maybe not like that, but they'll be diamond shapes. And if it's a 300 amp gun, the 3 diamonds will be filled in, so you'll know, and there'll be some empty diamonds, so you'll know that that's a 300 amp gun. Okay, and I don't care whose gun, I don't care who it's made by. In general, the industry standard is they're rated with 100% CO2. But you guys are using a mixed gas out there. So if this gun is rated 300 amps with 100% CO2, when you run a mixed gas like that through there, you have to lower the amount of amperage that gun can take. So now your 300 amp gun just became about a 225 amp gun. That's at 100%. All right? So if your gun starts getting really, really hot after you've welded some long welds and not giving it a chance to cool off, this contact tip, have you ever had it where it just whoop, just swallows that tip? Just stops it up, and that's it. And then you gotta try to unscrew it and pop the tip out. You've overheated, that gun's got so hot. You would think that hole would get bigger, but instead the hole gets smaller and you can feel it. You ever feel your gun start to shudder? Yeah, you can feel like you're holding a machine gun. You're like, oh, something bad is going to happen. That nose is getting ready to swallow that tip just like that. And within a minute or so, pretty soon, whoop, it'll swallow that tip. That's your indication. If your gun's so hot in your hands, even with gloves on, you need to go to Mike and say, hey, there's a problem here. I mean, you guys are responsible for the safety and the upkeep of these machines, okay? So if there's something wrong, check your grounds too. If you're getting a lot of spatter, a lot of porosity, check your ground. If you don't have a good ground, have you ever reached over to see your ground sparking?
You get really hot.
You know why it gets hot? That means energy that should be for your table here, and then your machines over here. You got leads going up here. the energy that's supposed to be going up to here is you're welding your ground. You're welding it either to the machine or you're welding it to the table. So the energy you think you're putting into here is really going into your ground. So if you're not getting good ground, or if you can't grab a hold of your cables, not necessarily the ground clamp, but that cable, if you can't put your hand on it for 3 seconds, something wrong. That's a safety issue. You tell somebody, these grounds aren't right, it's getting hot, somebody will get burned, something will happen. It'll start firing, okay? So be aware of that. All right, any questions? I can keep rambling on. Is there any questions you guys have? I mean, anything that you want to know, welding related, MIG, either wire, gas, machines, anything you want to know.
And you're going to spend some time with them on the floor too, right?
Absolutely. I'm going to go around and go individually if you have any questions and say, hey, if you don't want to ask them now, that's fine. Ask me when we get out there and say, hey, I always wondered, when I do this, this happens. I don't understand that. What does that mean? I'll be glad to try and help. I don't know if I'll have the answer, but I'll try. It's all about you guys learning and helping you be better at your job, making it easier so we got better quality. Okay? Any questions at all? None? We all know
Nozzle
what
gel, is it just something that we use, or nozzle gel, is it a good thing
Nozzle
or a
gel?
bad thing? I know it's to keep.
nozzle gel helps, but ideally, if you're doing the right thing and you're keeping the spatter, you're holding everything right, you shouldn't need that much. But, you know, if you want to, yes, you can try that to help keep it from coating. But not too much can be a problem too, because it gets up in there and it clogs it up, right?
Yeah.
So if you have to occasionally, maybe go ahead and use that, but I wouldn't say all the time. So
It seems
yeah,
that like it preserves that nickel plate. If you don't use it, then you're constantly
right.
digging and scraping.
Well, if you're
spatter.
getting a lot of spatter, then there's probably something else that we need to see. Okay, are we set right? Are our machine, is the amps and bolts set right? And hopefully Mike's got some procedures so you know within so many plus and minus wire feed speed with so much voltage, we know there should be a good setting. And if it's set right, we shouldn't be getting a ton of spatter. If you're getting a ton of spatter too, we didn't talk about this, but it'll get up into your torch. And if you don't clean out that torch, you're not getting gas through there, right? So if there's spatter, everything in there, the gas can't get down the nozzle. So you need to keep that clean. Anything else you guys can think of? Okay, all right, let's go out on the floor, or are we bringing the next group in? What do you want to do?
Let's the guys go back to work,
Okay,
and then after lunch,
okay,
be good if you make your rounds on the floor, because we got another group that needs to come in and we
Okay,
have lunch at
perfect.
11:30.
all right, guys, thank you, I
Thank
appreciate
you.
it. If you have any questions, I'll be out in a little bit.